Now let's have a look at let's summarize the Harris algorithm. What are the steps that need to be followed? And then we will ask a few questions about this. Is this working always when this is not working? Like in the case of Moravec, we saw the slanted edge and this was not working. Okay, we're going to reflect a little bit about this. Okay. So for the algorithm of Harris, the first step is just to compute the gradients. Remember, Ix and Iy, and I want to have this the partial derivative in x and y, and I use this. I do a convolution with my mask. Then I define a neighborhood around the point at which I'm going to compute the gradient. I'm going to compute its coordinates, sorry. And in this case, for instance, we have a 3 by 3 neighborhood. Okay? So this is Ix. Okay? This is the result of taking the derivative. So every point here, this is the gradient image. Sorry, in fact, is the partial derivative in the x direction, because the gradient is the combination of x and y. The partial derivative is in x and y. Okay, this is Ix. And here, this is the central pixel, which is this. I have a gradient in the x direction of 50 in this case. So I have a value of Ix of 50. Okay, it's this 50 here. Remember that what I want to do as a third step is to build the M matrix. And now I have these Ij values here. Why? Because I want, remember that I need to compute an M matrix for every pixel in my image. So I need to know, okay, in this case I'm in pixel Ij, located at position Ij. And what I need to do is to compute, in this case, the first element. Remember that there's a sum here. So this sum is telling me, okay, so I take the Ix and I do Ix square. But I don't take just this pixel here, this value here, because I want to be robust against noise. So what I do is I take this neighborhood, okay, this 3 by 3 window here, and I'm going to sum all these values. So this to the square, plus this to the square, plus this to the square, plus this to the square, and so on. Okay? And I get, so all this combination of values here. And this is what I'm going to put in the first column and first row of the M matrix. Okay? Then I will do the same with Iy, and I would compute this thing here, and now imagine I have Iy here, and I have the same window, so I'm going to take this to the square, plus this to the square, plus this to the square, and so on. And for the off-diagonal terms, I'm going to multiply this times this, plus this times this, and so on. Okay, and I'm going to get this M for pixel Ij, okay, this matrix. Once I have the matrix, what should I do? So one solution will be to find out what are the eigenvalues, lambda 1 and lambda 2, and then I could look at the eigenvalue that is smaller and just threshold this eigenvalue. Okay, this was what Harris and Stephens wanted to do. They didn't do it because they said this was too time consuming, because you have to compute the eigenvalues. But the ideal solution will be this one. Okay, then I compute the two eigenvalues, and I take the smaller eigenvalue, and I build this R image from the smaller eigenvalue for every pixel. Why is it taking the smaller eigenvalue? Because we said that a corner is detected if both eigenvalues are big. So should I just look at one eigenvalue, or I need to look at both of them? Of course, I need to look at both of them. But if I take the smaller one, and the smaller one is big enough, it means that both of them are big, aren't they? Yeah? So this is why it's taking the smaller eigenvalue. Okay, so I take the smaller eigenvalue, and then the only thing I need to do is just threshold this R image with the smaller eigenvalue. If I threshold it, any pixel that is bigger than this threshold should be a corner. All right? Okay. Remember, Harris and Stephens, instead of computing the eigenvalue, so this step 4, instead of doing the eigenvalue, they were using the determinant and the trace because the computation was faster and they thought that this was a good enough approximation. Yeah?
Nowadays, if you use that, are you using the eigenvalues and eigenvectors, or you are using the approximation?
That's a very good question. So nowadays, most libraries are still using the approximation. So if you take Harris from a library, the implementation that you'll find there probably is using the approximation. And the question you need to ask yourself is it worth using the approximation because of solving a square root nowadays with the computers that we have? Okay, you're going to play around with this in the lab session. So you tell me. Okay? And you will need also to tell me how good is this approximation. So is it a fair approximation? So, or is it performing the same or is it performing worse, to use the trace and the determinant? Okay? And how faster is it in nowadays computers? All right? So these are things that you will need to play around, and we can discuss this after the lab session. All right? But the point is very relevant, which is sometimes we do things because they have always been done like that, and it doesn't mean it's the best thing to do. Okay? So in the 80s, people implemented Harris algorithm with the approximation. It makes a lot of sense. But nowadays, it might not be the case. Okay, so let's move on. Let's see this example of a corner detection in an image in which, in this case, I'm setting a threshold of 25,000, and you see these are the corners. So anything that is bigger than 25,000 in the R image after computing this cornerness value of R, these are the corners that I detect. If I set a threshold of 10,000, look, some more points starting to appear. You see? Now I'm, for instance, I would say this. Look at this point here. It was not detected there, and it's detected here. Same for this other one that was not detected there. Okay, so depending on the threshold, and in this case, if I apply a threshold of 5,000, so there were corners that were not detected. For instance, look at this one here. This was not detected, and here is detected when I set the threshold to 5,000. So, but if I lower the threshold, funny things start happening. Look at this one here. Due to noise, this point is appearing here. I wouldn't never say that this point is a corner, because it's in a slanted, it's in an edge that has a given curvature. In this case, yeah.
Have you done a blurring before, or did you just computed the?
In this case, these are not my results. I'm not sure if there was a blurring carried out before, but probably not. Probably not. Normally, what you do, in fact, there's something I didn't tell you, which is when you compute the derivative, this sum of the derivative in x to the square. Remember, we have this. And we have ix, iy, and ix, iy. This matrix, normally, the way this is applied is applying this operation. And this is what you will do in the lab session. And this operation is a Gaussian smoothing. In fact, what this is saying is, so you don't take the derivatives in x to the square, but you do a Gaussian smoothing first. So it's a low-pass filter before that. Okay? So, but these things happen. So, and this is a big problem because, depending on what threshold I set, I can get more or less corners. But the nice thing is that if I look at the R image that I get, this R image is called the cornerness. The cornerness image. If I look at the cornerness image, the R image, the values that have higher that have higher scores in this cornerness image are more likely to be corners, okay, to be points that I will be able to detect in some other image after this moves around, okay. But I have a threshold issue. What is the threshold? I don't know. Okay, so I will need to fix this empirically.